Because in your end, you cannot. It seems like
I think I have to. I can.
I think it is already. I mean, do you see there on the top?
Yes, it is.
You tried to click it, right, Ryan, before?
I shared the screen and then I lost the.
Okay.
Yeah.
Right.
But it's recording. It's all good.
I think so. Yes. Yeah. So if
in the interest of time, should we? Yeah.
Is it okay for everybody that we record this session? For those of yes, I mean if someone does not accept it, you can tell us. But we had we tried to warn it in the website. So it would be great because I already know of a few people that wanted to join, but they cannot due to professional commitments. Okay, so thanks. Okay, so thank you so much. Look, shall we start, Ryan? Or I think let me see.
I think we should start.
Yes, I think we should start. Okay, let's start slowly. So, Ryan, so shall I give the word to you?
Sure. So, hi everyone. Thank you for joining us live, and hi to everyone who is watching this later on with the recording. Obviously, this presentation is focusing on our recent blind prediction competition. So today I'm just going to go over a few things, including just a quick overview and introduction of the tests that we performed. Also showing our own blind prediction results, and of course some of the results from all of the participants. I guess some of the highlights. What we're currently doing in terms of our current research focus using the large data set that has come from these tests. And also, of course, we announce the winners, and the winners will also have an opportunity to present the model and I guess how they actually came up with their predictions. Towards the end, we'll also give some other information as well as, I guess, hinting at maybe another blind prediction competition is just around the corner. So just a quick overview. Torsional actions in buildings subjected to earthquake ground motions are essentially inevitable. And of course, reinforced concrete U-shaped walls are a very popular in construction. So a good analogy of this is such as the building, the plan that's on your screen, where you have this U-shaped core wall that's essentially enclosing an elevator. It's on the periphery of the building. And of course, if you get strong north-south ground motions, as an example here, you can expect this building to essentially twist. So this wall will essentially be resisting all of those earthquake ground motions. And of course, very little research has actually gone into looking at the torsional performance and also the torsional capacity of such elements. So we conducted recently the experimental campaign. We looked at 3 different U-shaped wall specimens. And the first 2 of these specimens were the focus of the blind prediction competition. That was primarily just for timing. We wanted to give as much time to you as possible, although we know that it was only a couple of months, and I think that was over the summer break. So I think that was a little bit difficult for everyone. But yeah, so the first unit, UW1, was subjected to in-plane bending, so governed by flexure, and the second wall was, of course, rotated about its vertical axis, so with torsion. Just again, a quick summary. I know a lot of the participants are here with us, and you certainly already know this, but for everyone else, basically we wanted to make this a really complete blind prediction competition where we didn't just focus on things such as force and displacement. So we actually made this compulsory information. We called it compulsory information, where you essentially had to give these predictions to enter the competition. And these were, again, focusing on, let's say, strength and capacities. So if for the first wall unit was really focusing on force and displacement capacities, the second wall unit, of course, was focusing on torsion and rotation, so ultimate torques, for example. The second thing that we asked for, which we called optional information, was looking at more of the really local sort of performance of the wall. So things like the maximum tensile strain at a certain position or at a certain drift level, or the residual displacements for certain in-plane drift levels. And so we thought that these things, while they were very difficult to simulate, of course, you were rewarded a lot of other points if you had really good estimates. And we thought that that was really an exciting sort of opportunity to do this in our blind prediction competition that I guess was a little bit different from previous blind predictions. Okay, some quick videos. I hope that the bit rate of the internet here will actually show these reasonably well. But this first video is looking obviously above for the first wall specimen where we had the vertical actuators. So the vertical actuators were applying the axial load as well as the overturning moment. And you can see that there's two horizontal actuators at the back applying the horizontal force and displacements. This is a video from the back of the wall of the first wall unit. Again, you can see that these actuators were connected with the beam. That was primarily for the second wall specimen where we really needed that beam to increase the torque applied. So it wasn't really necessary for this first wall, but of course we wanted to keep the same test setup for all of the wall specimens. This third video, again, it's of the first wall specimen, but it's going to show where the failure occurs on this flange end, where you'll see some crushing failure and of course the buckling of the rebars. I think it accidentally just paused. So you'll see it there. The second wall unit, again, was rotated about its vertical axis in reverse cyclic motion. And this video will clearly show where the failure occurred. This was a little bit more complicated in terms of its failure mode than the first, and really required a lot of really observation in terms of how it actually failed, where did it fail. And you can read all this, by the way, in the report that we'll release after this presentation. In terms of our own blind prediction results, of course, we wanted a really good estimate of what sort of forces, what sort of displacements we were expecting to see in the experiment. We just did some simple pushover analyses, but using a fairly sophisticated program called Vector4. This is for the first wall specimen, so we had to model the actual shear span that we were applying. So instead of actually just making a model that was about 2.5 meters tall, we actually had to apply the entire shear span up to about 6.5 meters. And you can see that in comparison to the experimental results, it actually did reasonably well. It wasn't able to model the sort of the buckling that we observed at the boundary end, and so it did, I guess, overestimate the displacement capacities a little bit, and of course overestimated the forces a little bit. But overall, pretty good. And of course, once we have these experimental results, we can even get a much better result, right? By of course tweaking a few things and making it a little bit better. You'll see here as well, this red line is the SSM, which is the single story model. So that's when I actually have just the single story, the test unit height, and I've applied a force controlled analysis. So using all the forces that we actually applied experimentally. So this is the single story model instead of the actual model to the shear span. And of course, we use this model for the second wall specimen. This was our best guess in terms of the expected torque and rotation. And this is what we saw experimentally. So it actually really underestimated the torque that we got. And of course, it really overestimated the rotation capacities as well. And so what was really important for us in terms of modeling this was really modeling the head of the wall, where in previous numerical models where we had the wall just bending in flexure, we essentially made this head of the wall really, really stiff to remain elastic, which I guess it typically has throughout these experiments. But for this torsion, for this wall, we actually really had to relax that a little bit. And we got much better results, of course, once we had those experimental results. So we're still working on these numerical models, and we do plan to do a little bit of work in this area in the very near future. And I guess we'll have a little bit more to say on that towards the end of the presentation. So some of the results from different participants. So this is just an example of some force displacement response in terms of their envelopes. Again, I guess I've chosen some of the best examples, but you can clearly see that some different methods, and there were quite a lot of different methods used in terms of the software that was used, could really achieve a reasonable result in terms of its force displacement behavior. I should say that we had 15 applicants in total. And in the report, again, that we'll release, and I will actually send an email with this report to all of the participants and all of the registered users just after this presentation, it will show which program was used by which different participants. So for torque rotation, again, there were some reasonable estimates in terms of the torque rotation, but I guess that were a little bit less reasonable in comparison to the force displacement, which I think we really expected, again, considering that this really hasn't been the focus of many experimental or numerical research previously. One of the things that we do focus a little bit on here in our research team is residual displacements of reinforced concrete walls. And this was, of course, one thing that we did ask for in terms of the optional information. And so for those who aren't really aware of what residual displacements are, we're really looking at what the displacement achieved on returning back from an in-plane displacement or an in-plane drift. So when this force here is equal to 0, so that's your residual displacement. And we typically look at these as a function of the displacement or the drift that is achieved up here. So this is a plot of the residual displacements given by all of the different participants. The experimental is here in the sort of the black square symbols here. So again, you can see some participants really having some strong estimates in terms of in comparison to what we observed experimentally. I should say that this is the residual displacements towards the position where the wall failed for the first wall unit. We also had the residual displacements in the other direction as well, which makes really interesting sort of results. I should quickly just point out that this gray dashed line was from an expression that both João and I sort of derived earlier in the year when we looked at a really large data set of experimental walls, and we just simply took sort of an average line of all of these residual displacements. Something
Brian,
that was
maybe good
yes.
to note that I guess there are relatively few U-shaped walls there, right? I mean, that can partially explain the difference between.
I think there was a few things for why this is so different in terms of the difference between the experimental and the gray dash line. I should say that if you look at the residual displacements in the other direction, it's actually a very good match in terms of towards position D, which is really governed by those tensile strains in the flange end. I think the buckling that started occurring quite early on really affected these residual displacements in this direction. But yeah, certainly in this database, we used obviously a lot of different walls, but a lot of the walls that have been tested are certainly planar in terms of their cross section. That could be certainly one of the variabilities there. Okay, so one of the exciting things for our research team was the fact that we could use distributed fiber optic sensors. We attached this to 8 of the longitudinal bars in the wall. So what you're seeing on the screen here is actually a finite element model in terms of the grid, but the colors that you're seeing representing the different strains in the rebar are experimental measurements, okay? So all of these strains, and they're really high resolution. So the strains along the rebar length is about 3 meters, but we're seeing increments of strain of 0.65 millimeters. Okay, so 0.65 millimeters along the rebar, you essentially have a strain value. And importantly, into the foundation, which was a really cool thing to see the strain penetration into the foundation. This is how we were able to answer one of the optional information questions, which was what is the maximum tensile strain in the bars for a specific rotation and for a specific position. And so you can see here the black line is actually the average of the two rebars. And this blue, this white circle here is the maximum of the average, which is what we actually asked in the rule sheet. It was interesting to note that you've obviously got the dark blue profile here and the light blue. They're the two different strain profiles for the bars at this flange boundary end here. And so if we look at the strain profiles for the first wall, which was just pushed back and forth, the strain profiles are actually very, very similar. You really can't tell the difference between the two. But of course, when you have warping torsion and a little bit of circulatory torsion in these flanges, you really do see the difference in terms of the strain gradients through the thickness. Just a very quick note on, I guess, the current research focus here using the large data set, or I guess the large number of data that we got from the walls. We're really focusing on, well, now that we've got these strained within the wall, so in the core, how do they really compare with the surface measurements that we made with the wall with things such as the LVDTs, which is what you see on the screen here. So again, we had 8 rebars in total in terms of giving us a nice strain profile in the wall. How do they compare with things like the LVDTs on the surface? And I mean, this is just an obvious quick point where clearly you don't get that strain penetration with the LVDTs. And so you can really see the difference in terms of the strain profiles that you get. We're also making comparisons with things like the micrometers. So again, with surface measurements, you can clearly see the vertical displacement is quite different from what you see inside the wall with the distributed optical fiber sensors compared to the micrometers that you have in the wall. And lastly, we're also making comparisons with DIC, so with digital image correlation techniques. I won't go into too much detail here, but we're really using these measurements from the fiber optics to provide some sort of guidance in terms of what sort of gauge length or what sort of base length you should be averaging your digital image correlation results over to arrive at, I guess, strains and values that are more representative of what we actually see with large scale structures such as these walls. Okay. From here, I will actually hand it over to Joao. Joao, if you want to take it away.
Yeah, yes, thanks, Ryan. Actually, I was thinking, would it be the case that we ask for eventual possible questions right now, or should we maybe before we get into the funny part?
Sure, let me go back a slide then. Does anyone have any questions regarding anything that you've seen or anything of the walls in general? Don't be shy. I think you're all eager to find out who won then.
Okay, so if that's the case, let me pick over and let's. Okay, so drum rolls. So I do the easy part of the job. So the Oscar goes to. Actually, I should already say that the Oscar goes to both for the UW1, the first test unit, and the second. They go to the same, actually to the same team. And so Ryan, so it goes for the team that is composed by Marius Mavros, Juan Murciaverso, and Marius Panagiottou. And so actually, I think it's only Marius is from the University of Cyprus. Actually, there is and I think Juan is from Politecnica Catalunya, and Marius Panagiottou, he's I think he works for a private company at this point. So they have done an excellent job. Actually, I mean, I think we don't show it in this presentation, but I think it was the results for UW1. They were very, in terms of points, they were very similar to the second and to the third team that we will that I will present just right after. For UW2, the difference in terms of points was a little bit larger. So second and third place already moving. So for UW1, so we have from UCSD, so California, San Diego, we have Sergio Godinez, Andres Rodriguez, and Jose Restrepo, and then from the Hong Kong University of Science and Technology, we have Shenghan Zhang and Liang Liu, and from Switzerland, from the Federal Roads Office, Office Radboud, Raluca Constantin. Okay, so these are the first, second, and third place for UW1. Now, Ryan, we move for the second test unit. So from Canada, University of Waterloo, I see that Trevor is also here with us. Trevor, well, I may have some difficulties pronouncing your family name, but I guess Reinik, I'm sorry if this is not correct. And Alexander Kagermanov from also Switzerland, from the University of Applied Science in Rapperswil. So second and third place for the world that was subjected to torsion. Okay, so so now we asked Marius, so the winner of actually for both test units, to give us a small share with us a little bit the results, or let's say the details of his models. And so I will pass the screen to Marius, but I should actually just say right in up front that Marius will possibly already show you some results, some comparisons with the experimental results. So this was not because we gave him insights on the results. It was that once we contacted him and we told him that he was the winner, we gave him some information actually also for the second and third places. We shared like a preliminary and interim version of our report. So Marius, I think you're there, at least you were from the beginning. Can you hear us?
Yeah, hi Joao, can you hear me?
Hi, Marius. Thank you for preparing this presentation. This I guess it's just a few minutes, right? But
it's about, I think, 10 minutes.
10 minutes. So yeah. Please go ahead, share your screen.
Yeah, let me share my screen. So can you see my screen now?
Yes. Perfect.
Okay. First of all, I want to thank you, Ryan, Joao, for organizing this competition and gave us the floor to present our methodology. So my name is Marios Mavros. I'm a lecturer at the University of Cyprus, and my presentation today, I will give you a brief overview about the methodology we used for the blind prediction competition in collaboration with Professor Juan Murcia Delso from Universitat Politécnica de Catalunya and Dr. Marios Panagiotou from Nabin Youssef and Associates. So the analysis methodology we use is called BIM-TRAS model, or you can use the acronym BTM. And it was developed with the intention to simulate the behavior and to predict the failure modes of reinforced concrete wall systems, which are popular lateral load resisting systems used in many seismically active regions. Furthermore, BTM combines, as I will show later, conceptual simplicity and computational efficiency. Now, the failure modes of reinforced concrete walls observed in past earthquakes usually are more complex than the failure modes of beams and column members used in construction and can be affected by a multitude of damage patterns like flexural failure of the confined boundary regions in the form of concrete crushing followed by bar buckling and rupture, diagonal tension and compression failures with wave crushing, global out-of-plane buckling, and out-of-plane crushing of the walls. And here, allow me to give you a quick summary of how the method works, using as an example a portion of a T-shaped reinforced concrete wall. First, we discretize the section into smaller areas, and then we determine the areas of steel and concrete. Then the method uses vertical nonlinear fiber section beam elements to represent the vertical areas of concrete and steel. And exactly the same thing is happening in the horizontal direction with horizontal beams. Both horizontal and vertical beams have fibers that represent steel and concrete only along the thickness of the wall. Hence, they can develop only axial and out of plane stiffness. The in-plane stiffness now is coming from the inclined trusses. A critical part of this method is that the inclined trusses can model the diagonal compression field of concrete, accounting for biaxial effects. And this is done in the material level using a beta reduction factor that I will describe in the next slide. So for the concrete material law, we employ a constitutive model by Lou and Panagiotou, which can account for the strength degradation of unconfined concrete for uniaxial compression and tension. It can also account for the increased strength and ductility of confined concrete, and it also includes appropriate unloading, reloading rules to account for the cyclic hysteretic behavior of the material. As I said before, for the inclined truss elements, which represent the compressive field, we took into account the effect of the transverse tension in accordance with the modified compression field theory by Professor Vecchio and Collins. So the idea is that if we have an inclined truss with some compressive stress under the simultaneous existence of a transverse tensile strain, denoted here with epsilon n, the compressive stress of this element is multiplied by a reduction factor beta, which is a decreasing factor itself of the magnitude of the transverse tensile strain. Here I want to mention that since the material law involves softening, we included an automatic regularization procedure to prevent potential spurious mesh size effects. Now we use the material model by Kim and Koutroumanos for the reinforcing steel, which has been shown to be capable of capturing the monotonic tensile and cyclic hysteretic behavior of steel reinforcement. It accounts for buckling at the stress strain level by appropriate modification of the stress when a buckling criterion is met. And the model can also account for the bar rupture under monotonic or cyclic loading. We use an implementation of the BTM in the software FE Multi-Phys developed by Professor Koutroumanos at Virginia Tech. The main advantage of this implementation is that if we have what we call a BTM cell consisting of these 4 nodes arranged in this rectangular pattern with 2 vertical and 2 horizontal beam elements and 2 inclined truss elements, this cell is actually implemented under the hood as a 4-node shell element, facilitating that way an easier pre- and post-processing experience for the user. It is important to mention here that the capability of the BTM to capture all, let's say, important failure modes of reinforced concrete walls has been validated and demonstrated through a series of previous studies in the literature. For instance, here I'm showing some of these studies capturing diagonal tension, boundary crushing, and even global inelastic buckling failure that can happen in thin wall segments. Now let's move on with the analysis we performed for the blind prediction competition. Here you can see the mesh we use for both UW1 and UW2 models. The only difference between the 2 models were obviously the loading condition and the calibration of concrete material parameters. The light and dark gray color elements represent the unconfined and confined regions respectively. Here I want to mention that, as I will show later, our wrong assumption that the edges and corners of the walls are fully confined led to an overestimation of the ductility of UW1. In this plot, the uniaxial concrete law used for UW1 is shown, while the last 2 plots show the hysteretic behavior of the reinforcement for 6 and 12 millimeter bars, showing also the buckling and the rupture for a typical cyclic strain history. Finally, since we didn't model explicitly the footing of the specimen, we included a row of elements at the base to capture the strain penetration effect. For the UW1, the first test, the model was able to capture very well the force displacement hysteretic curves. However, it predicted a more ductile behavior and the strength degradation due to bar rupture at the instant indicated by the red arrow. The rupture was recorded at the edge of the flange during loading in the positive y direction. And here you can see also the stress strain curve of the 12mm bar, where the clear stress drop appears at the instant of the rupture. On the other hand, for UW2, the model underpredicted the torque capacity of the wall by about 10%. We have some thoughts on why this is happening, and when we have access to full experimental data, we will try to modify the methodology appropriately to capture this failure mode as well. However, the model did a really good job predicting the failure loading cycle when it happened, and the failure mode indicated by the hysteretic plot and the animation here, the same location that happened in the test. We also ran a post-competition analysis in order to understand why the model of UW1 predicted a more ductile behavior in the case of the UW1 specimen. As I said, we believe that what we overlooked at the blind prediction analysis was the fact that the specimen had walls that are only 10 centimeters thick, and the cover area in the confined regions that should be modeled as unconfined concrete constitute about 50% of that area. Hence, we modified the beam fiber section at the edges and the corners to include both confined and unconfined concrete. With only this modification, the updated model was able to better predict the failure mechanism and the failure displacement. And by looking the deformed mesh, someone can see also the buckling of the BTM element at the bottom edge of the wall. So as I said at the beginning of my presentation, I mentioned that the BTM is a computationally efficient methodology. In conjunction with the parallel capabilities of FE multi-phase, we managed to run the analysis of UW1 and UW2 that are fairly small models with 150 BTM shells and 180 nodes using four cores, in 16 and 35 minutes respectively. And in the plot, I'm showing the speed up we achieved by using multiple cores. This capability allows us to run full built-in systems. And in fact, we recently published a paper with static analysis on 14-story buildings that had about 9,000 BTM elements and 9,000 nodes. And we are now preparing the second paper with the dynamic analysis. And here you can see an animation of the most demanding, let's say, motion. This building had a core wall consisting of two couple U-shapes, similar to what was tested in the blind prediction. And what is important here is that we ran this analysis for the MC level earthquakes that push the structure well into the nonlinear region in a reasonable time frame. And before I give the floor back to Ryan and Joao, I want to acknowledge the general contribution of Professor Yannis Koudromanos from Virginia Tech, who is the developer of FE multi-phase, and he constantly updates the program based on our needs. BTM is only one of the methodologies included in the software. FE multi-phase can simulate steady state and time-dependent problems, and it can account for coupling among different processes like mechanical, thermal, chemical reaction, etc. Currently, it's compatible with 3 pre- and post-processing softwares, LS Pre-Post, ParaView, and GID. And as I showed before, it has parallel computational capabilities that are very easy to use. And one final thing that I want to bring into your attention is the new commercial software BTM component by Adstran. This software is a powerful pre- and post-processor dedicated to analysis of planar wall using the BTM methodology. And it uses, of course, the FE multi-phase as a solver. The user needs to only input some of the geometric, material characteristic, and loading conditions, and the software creates the mesh automatically with all the information needed for the vertical, horizontal, and inclined elements that I mentioned before. And at the end, it returns a nice report with the results indicating, for example, the failure modes and the maximum loads, etc. And with that, I want to close my presentation, and I will be happy to answer any questions that you may have.
Thank you, Marius, for this really excellent presentation. In a nutshell, it was very, very clear. I actually do have a couple of questions, but maybe let me first see if there is someone else who is curious about your model as well, who wants to ask a question first. Don't be shy. You can also use the chat if you prefer. But so maybe just Marius, there are two things that I was very curious. One is something that I have worked a little bit a few years ago, but then for many reasons I put it aside. But I was very curious. I see that maybe Trevor has one question. So Trevor, go ahead. That's my question after.
Yeah, sure. Marius, thanks for the very interesting presentation. And sorry here if it's a little noisy. It's Canadian Thanksgiving here in Canada, or the day after. So my kids are running around, hyped up on sugar and fatty food right now. Yeah, the truss beam methodology is really interesting. Obviously, it looks like it works quite well, and it's computationally efficient. I was curious if there's a 3D or more 3D version where you can actually have, like out of plane through thickness capability with your truss approach. And I'm envisioning like a cube or a solid that has truss or beam elements going from node to node. Does such a thing exist? Because I'm just, it seems like
I
you can
thought in
tackle a
the
lot
past,
of plane.
because we had some issues with the out of plane,
Yeah.
but in my knowledge, it doesn't exist yet, at least.
Okay.
We can capture some of the out of plane behavior because, as
Right.
I said, it's like beam elements. So at least the bending, the out of plane bending, we can capture it. And now we enhance the model to capture also the shear, the out of plane shear failure and shear degradation. But it needs an extra step of calibration. It's not like it's not happening automatically.
Yeah, no, because the speed is very appealing, and it'd be nice or interesting to see if such a thing could be done for punching type problems or something like that, right?
Yeah. Sure.
Anyway, very nice presentation. Thanks.
Thanks.
Excellent. Thanks, Trevor, for the question. Well, mine was not exactly out of plane. Actually, I was curious. I mean, did you for the UW? I mean, related to the question a little bit of Trevor, but for the UW1, you showed, at least it seemed in your in the animation, that there was some out of plane buckling, at least locally. Did you for some? Yes, yeah, exactly. So there we see in the bottom, right, that there is a little bit of. So did you, by any chance, I don't know, did you set a little bit of some slightly different properties in concrete on? No, it just came.
Slightly different. Sorry, I didn't wait for the question. Slightly different properties.
Yes, for example, on one side and the other of the in the same flange. So did you change it throughout the thickness, like because this was something that's like in several years ago when I was trying to use beam elements to model instability. I had to basically to define like, let's say I would do the yield stress a little bit lower from one side or the other in the thickness or thickness to basically trigger this instability or the out of plane instability in one direction, so that it would just start, let's say.
Yeah.
No, you did not.
So I did this analysis like the last days, so maybe I'm not sure if I had any mistake on those, but as far as I remember, I put like symmetric cross section.
And my other question was actually, I mean, because we exchanged, me and Marius, a couple of messages, and I was very interested in how you modeled the strain penetration, also because of all the results that we are obtaining with Ryan, right, with the optical fibers. So, Mario, how did you define the thickness? I think you said like 5 times the rebar diameter.
Yeah.
So that, and did you see? I mean, did you compare the results without modeling the strain penetration? Maybe you did not have time. I guess you did not have time to do this kind of comparisons. But did you see any difference?
I ran, I think, at the beginning, some analysis without the stream penetration.
Okay.
Obviously, the rupture was happening earlier, if I remember correctly, but now I cannot recall how we model the stream penetration. We use essentially some BTM elements that you see here, these short elements here,
Yes.
where we fixed all the nodes at the base, and at the top row of nodes, we have fixed all the degrees of freedom except the vertical degree of freedom. So this node can move up and down, but not in any other direction. And essentially, these BTMs have the same cross-section as the cross-section above it, with a little bit higher strength of concrete, so we don't mess up with any crushing in the footing, which we expect that is not going to happen. And the height of this element, I think it's from FIB that we took this estimation, about 5 dB. But I think also Juan is here, which is more expert in the stream penetration. I don't know if he wants to answer this question.
Yeah, thanks, Marios. Yeah, Mario suggested using 5 dB, and actually we had done some comparisons previously with this 5 dB where we assume constant strain penetration, right? With more, let's say, a little more accurate models, okay? And they were giving very similar results. So since the time was limited, we just decided to keep the 5 dB because we thought that it was a good match. Also, as Marios was mentioning, this is a value that appears in FIB model code for accounting for strain penetration effects.
Perfect. Thanks, Juan. Very clear. I really found it very, very ingenious the way that you have blocked and you just left really the vertical displacement and increasing the strength in the stiffness let's say in compression, right? Such that you would only have the behavior in tension, right? So this was really, really like the first time that I see this specific approach. I mean, we are always, I think, we are still a little bit lagging behind in these kind of models, but anyway. Any other questions to Marius from the floor? No questions. Okay, actually, I should say, I mean, I was just here taking some notes. You'll be able to see that in the report that we will send you. But the beam truss model was also used by the second, let's say the second place here for the UW1. So the one by Sergio, Andres, and Jose, if I'm not mistaken. They did not use multi-fees; they used OpenSeas. So, well, it seems like BTM seems, well, to provide very, very nice results. Whereas the other, so for the third place of UW1 and the second and third place, and correct me if I'm wrong, Ryan. So those, so third place of UW1 and the second and third of UW2, they all used shell models. Okay, so actually the two of them Vector 4 and the other, I think it was a program called, which I did not know, XDEEA by Alexander Kagermanov. Okay, so just for you to have, let's say an overview. It's correct, right, Ryan? I'm not saying any...
that's correct. Yeah.
Okay. Okay, so again, congratulations, Marius and Juan and the other Marius. I don't think he's here, and also to Ioannis Koutroumans. I think he at some point I think he joined us. I don't know if he's still there. Yes, he's. So excellent job, really very, very, very good job. Also, your simulations were very impressive. Also at the predicting local quantities, because this is really a big as a focus of our group, and I guess of our community in general, is to focus not just on the force displacement response, but what happens locally. And you did very, very impressive estimates also in terms of the strains, etc. So very, very good job. So Ryan, shall you maybe
I can share my screen again?
Yes, or I could also share mine, but if you have yours there. So I don't want to take also 45 minutes. So basically just to wrap up and to tease you a little bit for the next steps. So as Ryan said, and me as well, so the report, we will be releasing it today. We will email you to all of you. I think here all the people that are part of this chat are all participants. And you will be able also to download it from today or tomorrow. Maybe it's already available even on the website, okay, from our website. Then we are wrapping up a data paper regarding these experimental tests that we will submit it to Earthquake Spectra, and let's see. I mean, hopefully in the next couple of weeks we should submit it, and let's see how long it takes to be revised. I actually have to say that. As you may have realized, those of you when we were giving some updates on the website, we are not fully happy with the way that our experimental tests occurred or performed, because well, overall we are very happy. We have an excellent, I think we are an excellent team here also for our experimental tests, but we did have some problems with the construction of our specimens. So we have to resort to an outside company. And unfortunately, and especially for the UW3, the third unit, there were quite a few construction errors. And you may have already seen that in one of our first updates, the concrete covers. And this was for us, very penalizing and very, very heavy, because there are many dozen, hundreds of hours of work from Ryan, above all, also a little bit for me, but also technicians, engineers in the lab. And this was a little bit frustrating, but I guess those of you who do experimental tests, you possibly have some similar stories to tell. But anyway, so the paper we share with all the results associated to this paper. There will be the data set, which Ryan shows in the slide, with all the information that you may have with the pre-processed, or let's say the raw data, post-processed. Everything should be very, very clear. And not still the last bullet point, but almost the last, we will be preparing a journal special issue. Okay, still to be determined. We would like it to be open access. But well, let's see if we can also find, let's say, a journal that has minimum impact in the community, where the objective is really that it turns around, well, in principle, just this blind prediction simulation. We'll see if it would be possible to include the next one, which I'll tell you just in a second. But really, the idea is that we will invite, well, all of you are welcome, all the participants, even if you were not, say, ranked in the first three. But I mean, of course, we would like very much, at least for the three winning teams for each of the walls, that you could prepare, maybe give a contribution, not just with your, I think this is the interest for the community, not just with your predictions, let's say your original models, but also the tweaking and the tuning that you may do to your model once all the information is out, because I think it's there that we really can learn a lot on, well, what did we miss? What was the problem? Or was there something in the experiment, also some problem in the experiment that I did not actually capture? So this is something that we will be doing. So we will contact you. We will contact everybody. But of course, the first three, the winners will be. I mean, they'll be contacted, let's say, in first place, let's say. Okay, so blind prediction simulation post-test. And then we do have one surprise, which is not still 100% certain. So Ryan and I, we have introduced the proposal for some shake table tests, okay? And here you have an idea of, let's say, or a preliminary idea of the test unit. And so you see, you have, it's basically these walls are roughly 6 meters tall. You have there the unit, you have a scale there as a person, and you see that you may recognize the cross section. So the cross section that we intend, let's see if this, of course, if this is going to be financed. You know that this is far from being certain. but you may recognize the cross section. So it is exactly the same as the one of the current blind prediction test. And so we are talking about having a unit that has, let's say, on top masses of around maybe 30 tons, more or less. So all with also the weight of the wall, foundation, etc. We've been talking about an overall weight of around 40 tons. And so if these tests will go ahead, we will certainly be launching another blind prediction competition. So Marius, you were showing us some results of a paper that I'm already now interested in going to see, like this 14 story, if I understood well, 14 story building, also with the dynamic nonlinear response. So you have the chance to validate, hopefully validate your model very soon. Okay, so if this is funded, it will go relatively quickly, because so although we submitted like a couple of weeks ago this proposal, it is for the IRIS project, and I know that they will decide if they fund or not very quickly. So we will of course contact you all, preferably, and just for you to know, we do have, the idea is to have 2 specimens, and so this brings us to the last slide. So there will be 2 specimens. So the one now, this is just a small sketch to try to understand. So the one on the left is a, let's say, a common U-shaped RC unit, so with the reinforcing steel as reinforcement all over. And the second unit will be a unit where basically in the plastic hinge region and in the extremities of the so in the boundary elements, which, let's say, for the U-shaped wall will be, let's say, the corner regions of the walls, we will be using shape memory alloys, shape memory alloy rebars. And so what is really the idea? You see there a little bit in a very simplified way the difference between the stress strain curves and how they reflect in the let's say in the shear force or the lateral force, if you want, displacement. And so the difference between the shape memory alloys, for those who don't know, is that, well, they have a super elastic or pseudo elastic response. And so upon removal of stresses, there will be no plastic deformations, or there will be very little plastic deformations, and that is expected to be reflected also on lower residual displacements. Okay, so the idea, again, if this will be funded, is to compare the response between the 2 U-shaped walls, so one purely reinforced with steel, mild steel, and the other at the base changing partially or replacing partially some of the steel by these smart alloys. Okay, so I think this is all, Ryan. So we would be very happy to listen to your questions or comments. It was really, we are very thankful for all of your participation. We know that it was also, as Ryan said, it was not extremely convenient in the sense of timing. We gave you very small time to give us your predictions, and it was not just only a few weeks, but it was in the worst part of the year because it's when everybody goes on holidays. But, well, I mean, we have also many constraints in the lab, and then we wanted to present the part of the results in the European conference that was held in Bucharest like 3 weeks ago or 1 month ago. And so, but thank you so much. We had really participants coming from all over the world. I mean, and I see that that we have here also, I think, Bjarne, if I'm not mistaken. So all the team from Iceland to Canada, US, New Zealand. So it was, although, let's say, 15 participants, it was, let's say, not a massive number of participants, but I think it was a very, I mean, for us, for me and Ryan, it was very rewarding because there's many hours to put all these together, not just the tests, but all the competition. And so we are very thankful to all of you. And yes, Ryan, is there anything that you
No,
want to
I
add, or?
couldn't have said it any better. But I guess if anyone has any final questions before we finish up, we're obviously happy to answer. I'm so glad that we covered everything in this hour. Okay, well,
I mean, also the idea of
Yeah.
these let's say competitions and contests is not so much to compete, but I think it's more to open paths of collaboration between us, because we are such a small community, and if I think that if we don't get together, then we may, let's say, in the medium or long term, be easily kind of disappear among the other bigger concerns of society. So I think it's not so much to compete, but to be open to collaboration. So don't hesitate to, I mean, if you have ideas of collaboration, to not just to me and Ryan, but also within other participants that take part in these kind of events. Okay, so this is there's also a philosophical, let's say, a philosophical goal behind putting together these events.
Joao, Ryan, this is Juan. I just wanted to thank you guys for organizing this. I mean, it's a ton of work organizing, not only running the tests, which are impressive. So I think all the participants will agree with me that you guys did a great job, and thank you for we all learn from this, and we look forward to looking at the data when you publish the papers.
Thank you so much for
Thanks so much. Yeah.
Thank you for your comment, and really don't hesitate to contact, or if you want to address some of your colleagues, we can share some of the names maybe of the participants. Never, of course, the results, because this is only for the winners. But we are, let's say, happy to bring different people together in different parts of the world.
Yeah.
Okay, so. So that is it. So these the recordings will also make it available soon. Okay, so if you have other people, I know that some people did not manage to join us, so they'll be also available from our website. And yes, so stay tuned. Okay, for the next year, maybe we'll be seeing each other again. And again, thank you so much for all the work that you. I have a question. Yes, Bjarni, if I'm correct, if I'm pronouncing. Bjarni, you have to turn on your microphone. I didn't know what to say anything.
No, I don't have a question. I was just wanted to thank you for your contribution.
Thank you, Bjarni. Thank you for your participation. Okay, guys.
Okay.
Thank you, everybody, and see you soon. And we'll be in touch.
Thanks, everyone.
Thank you.
Bye.
Okay.
Bye.
Bye. Cheers.
Thanks everyone.
Thank you.
Cheers.